Hello there. This week we're going to be doing the last go of the regression, correlation and hypothesis testing stuff that we're going to do. We've done all the basic learning, but now we need to practice it and put some of the three different parts, because they're all sort of a little bit separate together. So we're going to just be practicing, which means doing all of the mixed exercise 1 on page 12. Looks like that. And what I'm going to do is I'd like to have a go at question 1 and 6 first. Now pause the video and then have a look as I work through it and check that you've got what's going on there, and then have a crack through the rest of the chapter and hope the rest of the exercise, and everything should be great. Okay, so first thing needed to work out this product moment correlation coefficient is to enter this data into a table. First mistake that could possibly be made is to forget to do the logs for each one. Now you can do that by going down and through and doing log 1.1, log 1.3, as you can see I did there. And then I thought, oh, let's have a little look and see whether or not we can put it straight in. And it turns out that you can. So if we go to statistics, and then on there you see it says 0.0413, which is actually log 1.1, and what I did was just put log 1.1 in there, and that comes up as 0.0413. so you can put the logs straight in, and that means you don't have to worry about getting degrees of accuracy and all that jazz, because it does it all for you. Okay, so once you put all of log 1.1, log 1.3 and so on down there, and then the same thing for list 2, you go calculate, so that's F2, and then reg x, and then either of these, remember, and we're looking for the R number. R equals 0.9998, so that's just part A sorted. So R equals 0.9998, and using your answer to explain why an equation in the form, that's a bit tricky to see, t equals ax to the power n is likely to be a good model for the relationship, is that the product moment correlation coefficient is very close to 1, which means that the data will fit very close to a line of best fit is all we need for that. Now the next part, the regression line, so they're telling us what that line of best fit would be. Determine the values of the constants a and n in the equation given in part B. Now I always like to go through the whole thing about just practicing about what's going on with logs, because the more you do this, the easier it's going to turn out to be, the more it will start to make sense. So if I take the log of both sides, that gives me log t equals log a x to the n, and then if I go again, I'm going to take a bit of a shortcut from what I've done before. I'm going to say the product rule would split it into log a plus log x to the power n, but sorry, the multiplicative rule would do that, and the product rule would turn log x to the power n to n log x. So what all of that means is that log a is going to be the y intercept, and n is what we're plotting it against log x, so n is being times by what our x axis is giving us, so that'll be the gradient. So that means that the n one is going to be really simple, because we can just say for the gradient n is going to equal 1.38, which is what's given us there. And then we also know that log a is going to be equal to so that's one answer, negative 0.210. So remembering our logs means 10 to the power a is going to equal 10 to the power negative 0.210. Get the calculator out, menu 1, and oh, I've already done it. 0.6165, so to 3 significant figures would be 0.617. And that is all of that. So have a little, yeah, that was part C, wasn't it? Have a crack at question 6, pause the video, and then I'll give you some help on that. Right, so calculating the product moment correlation coefficient, we go to 2 for statistics, and then it's simply a case of entering in all the data into the table, like so. And once it's all in there, double check that you've got all the right things in the right place. Hit calculate reg. Oh, hang on, I've gone too far. Right, then I hit that one instead. Right, hit the F1 for the AX plus B. You should have R equals 0.3401. So R equals 0.3401. It suggested there's no correlation between age and salary. Test this at the 5% significance level, stating your null and alternative hypothesis clearly. Well, your null hypothesis should be that there is no correlation between them, and your alternative hypothesis is going to be that there is one, so its probability is not 0, that one's going to affect the other. So because we're wanting to know that, we are looking at two tails. So your 5% has got to be split into a half at each end. What else do we need to know? We need to know how many, the sample size, and that is 10, and then 2.5%, we're looking at 0.025, aren't we? So remembering it's page 37 in the mathematical formula and statistical tables, and you're going for sample size 10 at 0.025, which is 0.6319. So that means that's the critical value of R is going to be, and remember it's plus or minus because it could be a negative correlation, 0.6319. So that means with only 10 bits of information, it needs to be showing up a lot more than it's doing there. So that's what we need to say next, is just to point out that 0.3401 is smaller than 0.6319. So that's tested it, and now we can say this means there is insufficient evidence to reject the null hypothesis at this level. Not actually, I'm going to grab that. I'm going to stop writing on that annoying paper as well. To reject the null hypothesis at 5%. Yeah, it's 5%, wasn't it? Yeah, 5 at a 5% significance level. Showing there is no correlation between age and salary. Of course there may be, really. We've only got 10 bits of data to look at, and if you look at everyone, there probably is some kind of correlation between age and salary, but it's probably there's probably a peak time to be earning lots of money, isn't there, and other ones, but never mind. That is our solution. So keep on going now, have a go at all the questions in that exercise, and hopefully it should just get easier and easier the more you do it. Okay, cheerio.